Me well. All right. Good evening, gentlemen, and good evening, everyone. I see quite a few people from outside Sri Lanka also. Welcome to this exciting presentation, exciting lesson on radio frequency signal propagation. Our main resource person for today is none other than our propagation expert, Victor Goonetilleke, 4S7 Victor Kilo. And this presentation is tailored or drafted having the examination, the Sri Lankan radio amateur examination in mind. But we made it open for anyone who's interested in the subject, and glad to see all of you who have joined today. So without wasting much any more time, let me start the presentation. And once I'm done with a couple of fundamentals, I'll hand over to Victor to go ahead with the propagation, which he knows way better than I do. As we all know, radio waves, just like any other electromagnetic wave, is a part of the electromagnetic spectrum. And just like the visible light or the ultraviolet or the X-rays, the radio waves also exhibit certain properties that are unique to electromagnetic waves. And before going there, the radio wave portion of the spectrum starts with very low frequencies, from couple of hertz in the very low frequency range, and goes up to like 100 gigahertz or more, which is in the extra high frequency range. And these electromagnetic radiations are made up of two fields, the electric and the magnetic field. And they are perpendicular, they oscillate perpendicular to each other. And the direction of propagation is also perpendicular to both of them. So if the electric and the magnetic fields oscillate perpendicular to each other, the direction of propagation is again orthogonal or perpendicular to the E and M fields. But for simplicity's sake, we only consider the electric field when we talk about electromagnetic waves and the polarity, the polarization, and certain other parameters. So only the electric field will be shown in future diagrams, but keep in mind that both electric and magnetic fields are there. Since this is a wave, particularly an electromagnetic wave, this also exhibits certain properties like the reflection, refraction, and diffraction. And there are a couple of more, but we are particularly interested in these three properties, behaviors. Reflection, as we all know, is the change of the direction of the wave when it is incident on a certain boundary. And we have to keep in mind that the angle that it makes with the normal or the incident surface, which is called the incident angle, is equal to the reflected angle. And refraction is the change of direction of the wave when they travel across a boundary. So they don't come back to the original medium, but they go through an interface and enters a second medium. And in diffraction, the waves spread out when they pass through a gap or an obstacle or an edge of a sharp object. All these properties will be useful when we talk about the behavior of radio waves. And as I mentioned earlier, the electromagnetic wave has two components, two fields, electric and the magnetic field. When we talk about the polarization, or the you must already know that there are two polarizations, mainly horizontal and vertical. So that polarization refers to the field, the electric field, which is in this case the horizontal direction, because the electric field is in the horizontal plane. Again, let me rephrase that. So the direction, or the polarization of an electric wave or a radio wave is the direction of the electric field, not the magnetic field. We talk only about the electric field. So two very famous, two very familiar antennas are shown here. One in the horizontal plane and on the other one in the vertical plane. So the first one on the far left is a Yagi, and it's the electric field is in the vertical plane, and on the other one the electric field lies on the horizontal plane. So in addition to this horizontal and vertical polarizations, there are a couple of other polarization techniques also. One other famous polarization is this circular polarization, which is mainly used for satellite communications. Because as we all know, satellites orbit around the Earth, and they also have their own trajectory. So the orbital position will be changes every time. So if we have an antenna pointing towards the space, a polarized antenna pointing towards the space, then once the orbital position changes, the satellite's position changes, there will be signal degradation, or we can't get the maximum use of the downlink signal or the uplink signal for that matter. So that's why we use circular polarization to mitigate this signal degradation caused by the polarization mismatch. And also there are certain ionospheric properties like this Faraday rotation, these phenomena that take place in the ionosphere. So to overcome or to mitigate the attenuations and signal degradation caused by those phenomena, we use circular polarization. And what happens if we use a wrong polarizer? If we use an antenna that is horizontally polarized to receive a vertically polarized signal, so that's where this cross polarization loss takes place. So usually it varies, but we as a rule of thumb, we usually take it as 20 dB loss. That is, if you use a horizontal antenna, for example, if you use a horizontal antenna to receive a vertical polarized signal, there will be a 20 dB loss, regardless of the all the space losses, the transmission losses, transmission line losses, and everything. But from the polarization itself, there will be a 20 dB loss. That means the received power will be 1/100th of the original power. Actually, so which is quite considerable. So before I know you are not here to listen to me all day. So before I hand it over to Victor, let me just play this small audio clip. I hope it will play well with the internet connection, and then I will hand over to Victor. He will take you through the rest of the journey, and I'm sure he'll share his personal experiences and how he got into this hobby of listening, shortwave listening, and how he studied propagation also. So please listen to this short audio clip.
Its first meeting of the year on February 28th.
Come in, come in. Don't worry about your muddy shoes. The shack is in the usual shambles anyway. I've been pretty busy these last few weeks because I'm involved in the celebrations of 100 years of British broadcasting, and our BBC Radio Club was able to get the special call sign GB100 BBC. Several members have been clocking up large numbers of contacts all over the world. But have a listen to this one. Our club member Abdul, operating the call sign, is in contact with Jalia, 4 Sierra 7 Juliet Lima / Maritime Mobile, a Sri Lankan radio ham on board a large container ship right in the middle of the North Atlantic.
Okay, call from 100 BBC, 4 Sugar 7 Lima Maritime Mobile from North Atlantic. Nice to work you up with your expression phone. Looks like belong to BBC and looks like celebrating the 100 years of BBC. I'm not sure. I don't have internet, but please give me the detail next over.
Yes, okay, Jalia. Yeah, no problem at all. Yeah, this is celebrating 100 years of the BBC. The call sign has been given to us for a year. When you do get the internet, there is a QRZ.com page
Okay, Abdul. Thank you very much for my contact. 70 please, and see you down the log.
Brilliant stuff, eh? What a fantastic thing to write into the log. And if you're a licensed radio ham, I do hope you'll have a chance to work our special call sign.
The Federal Communications Commission has posted an opening for an attorney advisor.
Hope you heard the audio clip clear enough. And with this, let's move on to our topic for the day. Victor, the stage is yours, and please continue with this presentation. I'll help you with the slides, Victor.
Okay. Good evening, John. Good evening, Taranga, and everybody else tonight, including Dr. Singh there. Good evening, and Anura, and the various guys, and also my good old friends, Jose Jacob, I think, is in India, and C.K. Raman, my regional boss of the Voice of America monitoring. Greetings to everybody. And tonight, I'd like to touch on a little bit of the fantastic, fascinating part of radio waves, or our amateur radio, our experimentation or pastime or whatever. I'm a little reluctant to call it a hobby, because I always say it's something which goes beyond the hobby. So thank you very much, Taranga, for the introduction. And I must pick up on Jalia's the contact with the BBC station there. And I'd like to tell you right now, tonight, and the nights, a few nights before, Jali on his massive container ship is steaming or going from New Zealand, his last port of call, towards Peru and to the Panama Canal. So he's right in the middle of the Pacific Ocean, and we have been in contact with him. Absolutely great. He's using just 10 watts or a little less than 10 watts and a vertical antenna, something like an 8-meter vertical antenna on board his container ship. And we've been contacting him, having absolutely delightful contacts in the last 4 or 5 evenings, and around 12 hours UTC. Now, all this is possible because we know when to contact, at what time, on what frequencies to make a two-way contact. If Jalia tells me, for instance, or somebody tells me, I'm in South America, I'm in Lima, Peru, Victor, I'd like to make a contact with you. And he says, I have only a 20-meter antenna. So we have to know radio propagation so that we can select the best time to make that two-way contact. Having even a kilowatt and the best of antennas will not take you very far, maybe a few kilometers out of your garden or your shack, if you don't know where to transmit, at what time, and on what frequency. Having said that, let me try to go through our presentation tonight. And it's a rather long presentation, so I'm not going to go very deep into every topic, but go through it. And maybe if I feel that we need to enlarge on certain topics, we'll try to do that. So now we have a generalized, on your screen, you'll have this slide, generalized model of communication system. Get the transmitted antenna, transmitter, line. I think all of you are familiar with that. If you have a transmitter, you have to have an antenna so that your transmitted power will get to the antenna, and a matchbox or a well-matched antenna. Otherwise, the power that you generate from the final stage of your transmitter will not radiate if you don't have a proper antenna. So antennas are very important, so that whatever frequency you're on, that antenna is matched to your transmitter and the frequency. Then on the receiving side, it's a reverse form. You have a receiving antenna, you pick up the signal. If you have an external antenna, maybe a tower or maybe on 2 trees, as we have in the tropical zones, or 2 coconut trees or whatever, and then a transmission line from the antenna down to your radio. And of course, the signal will be detected by your receiver. The modulation, it will be turned into audio signals and come out as audio signals, voice signals from your microphone or your headphones on your receiver. So you have the transmitter on the other side and you have the receiver. So in case you are the person transmitting, The other person, wherever he is, will be with his transceiver on receive mode to pick your transmission. And once you have finished transmitting, when you put it over to him, say my call sign 4S7VK, and I'm talking to, we'll say, my good friend Jalia, who is in the middle of the South Pacific, 4S7JL. So when I say 4S7JL, take it over, say 4S7JL, this is 4S7VK, over. Then he will be transmitting, I will receive. So this is the two-way process that we have in communications. Can we go on to the next slide, Taranga? Okay. Sorry. Then we have the key factors influencing radio propagation. You have, I think at this stage, I must go back to our ancestors who worship the sun. Actually, all radio amateurs or people who are interested in communications, we are more or less sun worshippers. If the sun goes off, if we lose the sun, there won't be radio propagation. It's one of the most important, if not the most important factor in two-way communications. Of course, on high frequencies, even if the sun is not there, on a VHF or a UHF rigs, handhelds, within say a half a kilometer or whatever line of sight, you will be able to communicate. But long distance communications, beyond the line of sight, where we come into what is most important, covering distances, and in disasters, how we communicate, that all that becomes influenced by the sun or the ionospheric conditions. So we have ionospheric propagation, which will be affected short-term and long-term. For instance, you have the solar activity, the sun, the effect of the sun, which is seasonal. For instance, during summer, you will have the influence of the sun more above you and close to you. During the winter, we'll have less. And it goes the same way. If the sun has so much of an influence, then there will be day and night variations. During the day, certain bands will be very good. And as night approaches, those frequency bands might start going down and even totally disappear. And again, if the sun is the main factor, we talked about day and night, then the seasons, summer, winter, spring, as you know, the effects on the ionosphere will vary during summer, and it will start going down to autumn, winter, and then spring and come back. So the cycle will go on a seasonal basis. And at the same time, the day, at high noon, we have the maximum ionization on the ionosphere, on the layers. And as we go away from noon, it will start going down. And at sunset, it will be minimum. And then again, at daybreak or sunrise, it will start affecting more and more. So you have the day-night effect, you have the seasonal effect, and you also have what you call the solar cycle, the 11-year solar cycle. Again, we have scientists have observed for more than 100 or 200 years that the sun's effect, there's an 11 years, approximately something like 10.5 to 12 years, a solar cycle from minimum, maximum down to a minimum. A complete cycle will be 11 years approximately. Some solar cycles have been found to go off around 10.5 years, and another sometimes a little prolonged 12 years. So what happens is when one cycle is going down, coming down to the minimum, the next cycle begins. So there is a little bit of an overlap sometimes. The minimum one cycle, this is cycle 21 and cycle 22. As the cycle 21 goes off, 22 will start. So there is no space between cycles where the sun will be completely off affecting until the next cycle starts. So the cycles at the beginning or the end, they overlap a little bit. And then the new cycle starts going off. We are in cycle 25, as we know now. So And the other effects of the signals can be, now that is high frequency, effect of the high frequencies, where the signals bouncing off the ionosphere. So as you know, as I mentioned before, the ionosphere is affected, or radio signal transmission is affected by the factors of the sun, how much solar radiation, ultraviolet radiation falls on the layers above us. So, or between two signal locations, receive and transmit. So then we are also talking about line of sight, or UHF or VHF propagation, and even the gigahertz areas and all that. Then those become line of sight, which means you have the receiving signal antenna and the transmitting antenna have to almost virtually see each other. So that's why if we have two walkie-talkies, we will stop hearing another person, say after about 200-300 meters or 1 kilometer, depending on the terrain. If you're on the shore, see, there's a boat a kilometer away, you'll still be able to communicate with him because there are no obstructions. Then we have obstructions that come in to stop this line of sight signal. There could be tall buildings. If you're at the foot of a building and a huge shopping complex or a housing complex is in front of you and towering up to maybe 100 or 200 feet above, or say 75 meters from the ground, and your other person is on the other side of the building, you will find that the signal is getting blocked, or it's because of the high building. The same thing can happen depending on the terrain. If there is a mountain range, or if you're at the foot of a mountain and there's another friend on the valley on the other side, you might find that you'll not be able to communicate, or maybe just signals which are very scratchy and which might bounce off other areas. Or if your friend is directly in front of you and you have a building in front of you, between you, which is blocking the signal. However, radio signals don't penetrate in a pencil line and not anywhere else. Of course, with a beam, you can direct your signals, but it may be that there is another building behind you and your signal might bounce off that over this obstructing building and reach your friend. That is possible. In the same way, one thing I must tell you, when a radio signal takes off from your antenna, we have no absolute 100% knowledge of how it gets to the other point. We have a very accurate or sure understanding of radio signals, but it doesn't mean that it is this and nothing else. So signals can be refracted, they can be reflected from buildings, mountain ranges, and even aircraft, somebody flying above you. I think we'll come to that later, but just to touch on that, just as I said, I was in the city of Colombo, and our repeater, we had a repeater in Colombo on the overseas telecommunications tower. And there was this big building which was blocking my signal reaching that repeater. Suddenly, and between that obstruction and my location, we had the Sri Lanka Air Force Colombo base. And suddenly, I heard a helicopter coming down, and my signal started hitting the repeater in a fluttery way. And the moment the helicopter came down, my signal also disappeared. So, as a temporary bouncing or refracting or reflecting item, that helicopter helped me. And this has been observed by radio amateurs. There have been scheduled flights from, for instance, Ratwalana in Sri Lanka, one of our coastal city airports, a flight taking off to Trincomalee, right across the island. And radio amateurs have noticed that as this aircraft, an old Dakota, I think DC-8 or whatever, old twin-propelled aircraft, as it flew, they were waiting for it, and as they passed between the two locations of the VHF, the receiver and the transmitted signal transmitter, or the guy transmitting, there was a flutter of the signal as the aircraft passed. So, radio signal propagation, whether it is line of sight Or if you have a repeater on a high mountain, as we have in Sri Lanka, the highest mountain in Sri Lanka is Mount Pidrutalagala, towering more than 8,000 feet above main sea level. And we have a repeater up there. So if I can't talk to somebody 15 kilometers away with two handhelds on the ground level, I can get back to him hitting the repeater up on that mountain, because there is no obstruction between that repeater at 8,000 feet and my location right here in Colombo. Although as a direct signal, I might not be able to reach somebody just 25 kilometers from my location. So that's a repeater. In the same way, if we have satellites high up over the orbiting, some are orbiting satellites, amateur satellites, some are geostationary satellites put there. Concept by great Arthur C. Clarke. We are very happy, proud of him that he was in Sri Lanka as a whole British scientist, but he came up with this concept of satellite communications. As you all, I'm sure you know, I don't have to go into it, but just to mention that great man. So with geostationary satellites placed high up, it is possible for us to achieve this phenomenon of line of sight. So repeaters, satellites, two people on one on a high mountain, more or less like a repeater, it's possible. So I have touched on the modes of communication and how it will affect the sun and the terrestrial disturbances and all that. Then we'll go on. Next is the type of propagation, skywave propagation. I think that is the most fascinating if you are thinking of international communications from operator to operator without the intervention of satellites. Or today we have Echolink in ham radio, or you have the computer, internet-based WhatsApp or Zoom, as we are on now on this presentation. But we're talking about a person-to-person without satellites. At the moment, we are talking about skywave propagation, where my signal takes off from my antenna and goes skywards. And it has to come down at some point because it will be refracted or refracted off the ionosphere, which is this charged layer above the Earth. So that's why we call it a skywave. Radio waves traveling upwards are bent or refracted by ionosphere back to Earth. So you have it there on the slide. I'm not 100% looking at the slide sometimes, but just going on so that we can save time. So virtually all long-distance radio communications from 80 to 10 meters, that's approximately 80, that's 3.5 megahertz, up to 10 meters, 28 megahertz. But below that, we have 1.6 or 1.8 megahertz, the 160 meter fascinating band, we call the top band, if I'm not mistaken. Sorry, sometimes I might get a little mixed up with my terminology, excuse me, but lowest band, where you need very high antennas, the noise level is high, but that's where the experienced guys, the people who accept challenges of long distance, low power propagation delves in. So then we have the VHF and the higher band frequency, mostly directly related to wave propagation or line of sight. Then we have ground wave propagation. That is, when you emit a signal from my transmitter, most of it will say go up skywards, but there is also, you can't stop a radio signal from radiating in different areas. Of course, using a beam antenna, you can project your signal or beam your signal in a desired direction. But that doesn't mean the best of antennas cannot stop some power going in all directions. So that is along the ground wave. You see, have a signal hugging the ground. And this ground wave signal can travel up to about 50 kilometers, again, depending on the terrain. If you're on the sea, like earlier, on a maritime mobile, his signal will go further. because we have found that attenuation or absorption or degeneration of signals is much higher on land than over the waters, the sea. So the ground wave, now if for instance I'm in Colombo and I transmit a skywave signal, yes, it will hit the sky and come down somewhere, but at the same time my signal will also, some of it will be traveling along the ground, and the ground wave signal will get attenuated for the Earth's absorption, and also during the day, the delay and all that. And after about 30, 40 kilometers, and also depending on your power. If you're using very low power, your ground wave might go 5 kilometers. But if you're using 100 watts or maybe 500 watts, I'm talking as a radio amateur, not so much as a broadcaster using 250 kilowatts. Maybe later on I'll come there briefly, but tonight I think we are concentrating mainly on amateur radio transmission. So our power levels are 100, 500 watts, maybe a kilowatt. Some, of course, I know Americans are allowed 2 kilowatts, but just let's talk about 100 watts or below. So if you're using 100 watts, your ground wave signal will go further because the attenuation will take you further than a low wattage transmitter, which will get completely wiped out after about 4 or 5 kilometers. And then you have the point at which your skywave signal hits the ionosphere and is refracted back to Earth. And at that point is the point that your signal, skywave signal, comes down to Earth. And how long, how distant will your signal go depends on the ionosphere, time of day, and also your antenna. So we'll say your signal strikes somewhere 600 kilometers from your location. And that's the first point, your hop. A single hop can take you up to about 60 kilometers or so and beyond. A single hop, it's estimated that will cover about 3,500 to 4,000 kilometers. So now the point that we are talking about is you get this on the diagram skip zone and the skip distance. So the ground wave will take you up to about, we'll say 50 kilometers, and then there's no signal. It drops. And your skywave comes down at 800 kilometers from your location. And so you will know that there is an area that has no signal. So that's the skip zone, or the skip distance is measured from the graph, from the point where you're transmitting and where your signal comes down. And if you disregard the ground wave, that distance is the skip distance. So next, let's see. So then then you have in the HF bands and above, the radio waves are attenuated by the Earth's surface. And then we are going into the higher HF, above the high frequencies, into the VHF and UHF range. But I'll stick to HF for the moment, because without mixing up too many modes. So on high frequencies, now your signal will depend, as I said, we are not talking about the ground wave. We have spoken about that, a short distance, and the first point at which your signal comes down, and the area between that, there's a silent zone, which we call the skip zone. And the distance between the transmitter and that point is called the skip distance. Then, can you have the next slide, Taranga?
Victor, I changed the slides.
Yeah, I'm on ground wave propagation.
Okay, hold on.
Okay, right. Now I come to, yeah, it has come. Maybe internet is slow for me. Right, skip distance. The distance transmitted location and the point that the skywave. So I think we've covered that. So probably that's clear enough. Now, if you look at the diagram, then skywave propagation, we are coming into skywave propagation now. beginning with VLF or very VHF and UHF frequencies, then direct and refracted waves are okay. Now I spoke to you about, because we have so many slides to cover and you'll have this presentation, I'm going through quickly so that to save time and not to make this a boring long 2 or 3 hour session, which I don't want to. So we spoke about VHF, how, you know, with 2 handhelds we can communicate. And if you're on a mountain top, how the line of sight increases, that's a VHF and UHF, and how we can have a repeater and enhance the distance even more. And also using satellites, we can have television and other means of data and voice transmissions. Okay, now we come to the layers of the ionosphere. Right. We have in the ionosphere, the lowest layer close to the Earth is called the D region. Now somebody will ask me briefly, why do you call it the D? Isn't there an A, B, C? Well, the simple answer to that I have received is that let's keep A, B, and C in case someday we discover another layer. Okay, we start with the D layer. And just above the D layer, we have the E layer. And you will see the distances. I'm not going to read all these things and waste your time, but you can have a look. So you have the D layer above the Earth, which is about 70 to 80 miles, kilometers. And then above that, we have the E layer. And then we have the F region of the air. We have 2 layers, F1 and F2. Now, during the daytime, these 2 layers, F1 and you have F2 layers. Now, these are the 2 layers which are the most important for long distance, high frequency or HF propagation. And at night, after sunset, what happens is F1 and F2 merge together to create a single F region. Now, if you asked a question at the examination, at night, do you have F1 and F2, or you have the E layer, or D layer, or you have one F layer, then your answer will be F1 layer, because at night, after sunset, quickly, before sunrise, these 2 layers combine to form a single F layer. Then, okay, now you have the distances, F1, F2 layer, 320 kilometers above the ground, above the Earth. And then nighttime, how the D layer disappears. You know, as we approach sunset, the D layer disappears. The D layer is a daytime layer. And the D layer is a hindrance, and it absorbs signals, while the E layer helps us limited way to bounce our signals depending on the time of the year and day. We can have E layer propagation. I think later on in the slides, we'll have sporadic E, how sporadically we have E clouds. But to concentrate on long distance propagation, we depend on the F layer. And so our signal, which takes off from our transmitter and heads towards the ionosphere, hits the F1 or F2 layer, depending on the time of day and the density of the layers. It will strike the ionosphere and it will be refracted back to Earth. And that is what gives us a point-to-point communication. From Sri Lanka to go towards India, Pakistan, the Middle East, and beyond, the skywave, striking the F layers and beyond. So what happens is our signal strikes the F layer, comes down, and we have estimated the maximum distance that a single hop, taking off, striking the ionosphere, and coming down to Earth is what we call a hop, a single hop. So a single hop is estimated to cover about 2,500 miles or we'll stick to kilometers, approximately anything between 3,500 to about 4,200 kilometers. So if your target is 8,000 kilometers away, then you will need 2 hops at least to cover that distance. So you must know the ionospheric conditions, the conditions of the ionosphere at that particular time of day, so that your signal will come down at the first hop, bounce off the Earth in the same manner that it strikes, comes down from the F layer. It will bounce off again towards the F layer, ionosphere, hit the ionosphere, and come down. In that way, it is possible to go right round the world, hopping maybe 10 or 12 hops, depending on your antenna, time of day. But we have found that the ionosphere is not the same in all parts of the world at any given time. If it is 12 noon in Sri Lanka, it might be 4 o'clock or 5 o'clock in the afternoon, evening, early evening in Australia, and the sun is affecting the layer much less there. And beyond Australia, it's in total darkness. In the same way, if we go west of Sri Lanka, at high noon here, you go 5 hours from Sri Lanka, you go to the European region, and it's still getting up early morning, 5 hours from, say, about 10 o'clock or say 8 o'clock or 6 o'clock or whatever, 5 hours from. So the ionospheric effect between the paths will vary from geographical location to location. So then comes, how do we establish communication? If the sun, which is affecting my location, the transmitting location, and I want to reach, we'll say England, London, and I need 3 hops to get there. It has to go up, come down somewhere in the Gulf, another hop, go towards the Mediterranean, and the third hop coming down in London or the British Isles. And how will you know what the conditions would be between Sri Lanka and London at any given time of day? Because when I put my transmitter and I beam towards England, I must know what band I must use to communicate, to establish communication. My signal must hit the ionosphere, come down, go up again, come down, and not get lost, not get absorbed. It should bounce again. So the conditions between Sri Lanka or London or any 2 points that we want to communicate with, we should have ionospheric propagation to reach that point. Now, how do we establish that condition? How would we know what band and what frequency to use? Now, that is what the radio amateur has to do. Learn. Of course, there are many radio amateurs. They would just take a transmitter, get a good antenna, and just, tune around. And when they hear a signal, of course, it goes without saying, if you hear a signal, there is 80 or 90% chance that that guy will hear you if your antenna and your power levels are, we'll say, approximately the same. So you can either hit or miss. So that's not being very practical, or no, that's not being very experimental in our way. Because in an emergency, if you are going to dial around, see whether I'm going to catch somebody on 20 meters or whether it's 50, you can't do that. You have to know your onions in propagation. And it's not a very difficult thing if you take a little trouble over it. Now, can we go on to the next slide, Taranga? Yeah, we have the sunspots and their impact on the ionosphere. Now, I told you that we must determine how we can establish communication between these 2 points. Now, to know that, we have to also realize that the sunspots and the time of year, the effect of the sun. Now, the sunspots, I think most of you, since you are interested in radio, not rank amateurs, you are conversant with the subject, you're trying to seek more on this topic. You know, the sun has this solar activity, 11-year sunspot cycle, and the number of solar spots can increase or decrease during that cycle. Then sunspot increases the sun's radiation, including ultraviolet ray. So when there are more sunspots on the surface of the sun, it emits, it sends out ultraviolet radiation and power, energy out of the sun, and we are in the sun's influence. And the ionosphere receives this ultraviolet radiation and the solar radiation, and that charges up the ionosphere. So the more sunspots on the sun, obviously, ionization will be greater. Higher sunspot activity, more intense atmospheric ionization. Sunspot activity cycles approximately 11 years, maximum 6,200. And sunspots, they say maximum activity 60 sunspots to 200 sunspots. But there are short area periods when you will not see a single sunspot on the surface of the sun. And at that time, you can expect very low propagation conditions, especially on the higher bands. High sunspot, enhanced skywave propagation at higher. Now, okay, I'm going to skip the slide, or rather, summarize the slide quickly. Now, high frequency propagation, we have observed that if you take, we'll say, we're talking about 80 meters, we'll say 3 megahertz, and on the high end, 28 megahertz, I will say 30 megahertz, 3 to 30, to remember easy, 3 to 30 megahertz. 30 megahertz, we call it the high end of the our HF high frequency spectrum, and 3 megahertz and below will be the low area. Now, a rule of thumb, just to remember easily, between 3 and we'll say 10 megahertz, 3 and 10 megahertz. Sorry, I think I mixed up megahertz and meter. Okay, 3.5 megahertz. And the high end is 28 megahertz, right? So 3.5 till about 10 megahertz, we call it the low frequency end, the low end. The low end, which is usually affected more by daylight and heavy ionization, and therefore it is best during periods of darkness. So 3.5 megahertz to 10 megahertz, we call that more or less a nighttime range. Then from about 10 megahertz, now you start going up. Then you have 14 megahertz, which is the 20-meter band, 14 megahertz. Then we get the new WRC 18 megahertz. Up to around that band, 10 to 18, it's a day-night band. It's a day-night band. We come to that, why we call it a day-night band. And then above, we'll say 18, that's 21 megahertz, 24 megahertz, 28 megahertz. Or if you are going by meter bands, 10 meters, down 12 meters, 13 meters. So coming down, that the meter bands on your transit. So, but we'll just not mix up meters and megahertz. So the high end above 18 propagates very well during periods of daylight. And why is that? Because that high end needs a lot of ionization. So I think you can easily now come to the point, if it needs high ionization, when do we have high ionization? during high solar activity. When the sunspot cycle is at its peak or the high side of it, then solar radiation is more. Then those high frequencies, 21 megahertz, 24, 28 will propagate better. And also it goes without saying, during darkness, there is less ionization. Naturally, those bands will perform less after night time. And also season. During the summer season, it will perform better than in the winter. In the same way, we come to that mid-range, 10 to 18 megahertz area. What happens is, we said that is a day-night band. During the daytime, the distances that you can cover will be greater than coming close to night time. At night time, as I said, the high ionization or mid-high ionization you need for the higher end of that mid-range will start dropping because we are coming close to sunset, or it's winter, or it's the low sunspot cycle years. And then at that same range, the low end of that band, like 10, 11, will propagate better as we come closer to the evening. And then after sunset, we'll find that the low area, 3.5 to 10, we'll say 7 megahertz, 8 megahertz, that area, which is absorbed, signals in those areas are absorbed by high ionization. So just as much as the higher end needs more ionization, the low end needs less, because the low end gets absorbed in the ionosphere if the sunspot, the solar radiation is high. So during night, those low frequencies perform better, while the high-end frequencies perform better during daytime, noontime, and periods when the two stations are in daylight. In the same way, the low-end stations will perform best when both the transmitter and the receiver are in darkness or coming close to twilight. So you see that the range now, the low end needs less ionization, the mid-range needs day-night, and the high end needs a lot of ionization. And so, because it needs a lot of ionization, during summer months, during the height of the solar cycle, and also during daytime. So day seasons, summer and the cycle, will determine that the higher end is better. In the same way, the opposite direction, during the low sunspot cycle, the low frequencies perform better. At night time, they perform better. At winter time, they perform better because there's less absorption. And the high end performs better because there's more refraction. So observed for 250 years. So our scientists have been observing the solar cycle for almost 250 years. And taking these observations, we have come to certain, assumptions that the solar cycle is from one to the other. It's about 11 years or 12 years maximum, or 10 years, between 10 and 12 years. And the solar cycles, 25 began in 2000. So our radio amateurs always say, oh, we are at the bottom of the cycle, so long distance propagation is difficult because there is less ionization during the low solar cycle, because the effect of the sun on the ionosphere is less during the low part of the solar cycle. At the same time, if you have night time, winter time, and low sunspot years, you will find that hardly anything is there after dark on 21 megahertz or above. And the bands are very active on the low end. 160 meters, people wait for winter time or night time and the low sunspot cycle to work. Now, a lot of people, these are common things, say, oh, we are down on the sunspot cycle, it's useless getting on the band. Now, the people who say that are people who rely on the higher part of the band, whereas the real people who make the challenge of working long distance on low frequencies with the absorption and all that, and also you need very big antennas. So the real boys are on the low frequencies, and they wait for the low sunspot cycle for December, January, February in the northern hemisphere, and in the same way the other months in the southern hemisphere. So now you see how this sunspot cycle, the time of year and also time of day affect the possibility of communicating on the high frequency bands. So now, if you study that, if you have an understanding of that, you will be able to make maximum use of the radio signals to reach your target wherever you want to communicate with. Remember, before the satellites came in, we relied on telex machines, sorry, HF radio telephones. So our engineers, not only radio amateurs, engineers in the government or the telecommunications, the post and telecommunications department, they had to know their propagation. How? If you want to make a radio telephone contact, because we had no internet and all that, of course, there were undersea cables and all that, but then those circuits were limited. If you wanted to use a radio phone, or if you're on a ship, voice, you had to know what bands to use. So propagation, study of propagation, not only is a fantastic, fascinating feature, it is also the main feature of two-way communications using high frequencies and the ionosphere. And of course, now we have the internet and satellites and all that. But when everything fails, then you have to depend on the ionosphere. And those who can use the ionosphere, knowledge of it, will know that they are not limited by your mobile phone or your computer and the networks. So you're on your own, wherever you are. Just like we experienced that during the tsunami, the whole coastal belt got completely wiped out. There wasn't a single mobile antenna or mobile station active. The ship to shore, the police, the Navy stations, communication stations were wiped out. And it was only high frequency radio, HF radio, and the radio hams who knew their propagation, what band to use from what point to what point in Sri Lanka or the world. And so this is a fascinating and an important thing. Okay, then we go on to, now how do we know what the ionospheric conditions are? Who tells you that we are in the sunspot maximum or minimum? I mean, as a radio amateur, do you have some device in your home, like a thermometer or some blessed meter, to know whether we are in the high sunspot cycle or low sunspot cycle end, or what the level of ionization is, so that we will be able to make use of that data and establish our two-way communication. Now, scientists, not of course radio amateurs, scientists with, telescopes and all those things, observing the sunspot, the sun's radiation and all that, they have devised certain measurements. And you have got the A and K indices measuring geomagnetic activity. You get the A index. Now, these things may not sort of go straight into your mind, as you know, you will need to look at it more often, get familiar with it as you go along. But for your purposes, for information, it's important. It will be good for you to know that the A index, you have the A index, which is a daily average of geomagnetic disturbance levels, right? So these scientific stations, whether they are in the tropics or in the more temperate zones, or even down in the Arctic or Antarctic weather stations, they take these measurements and they combine this data and they come into an index, A index, daily average. And then you have the K index, measures maximum magnetic fluctuations over 3-hour intervals. So A is a short term, I mean, if you take the day, A index, average of the day. Now, if you look at the A index, represent fluctuations from quiet day curve, and you get the distances there. So, shall we go on to the next slide, please? Yeah. Now, taking all this, the data, please go through that data, the previous slide, as you see, and, quietly go through it, read it, and try to absorb it, because it is not possible for me to make it go into your mind straight away, just like taking a pill or whatever. So, all that data is brought into this general relationship, that is an A index and K index. Now, A is the general index of a daytime average, and the K index is 3-hour. Now, you have what you call propagation forecasts. You have it given on the radio. Now, if you listen to the US stations in Hawaii, and also Fort Collins in Colorado, you have time and frequency stations which give out a propagation forecast every day, a few hours a day. And also, that was during the time when we had only radio. But now we have the internet. So on the slide, you will see at the bottom, you will see a report which gives the condition. Now you'll see the amateur bands there from 10 meters down. So that is done for you. So it gives you the data, the K index and the A index. And to make it even easier, they have determined whether these bands are open now or not, because they have taken the A, K index, time of day and all that. But you must be able to get your own prediction. And to do that, yes, you can go through that guide, and also you can take the K and the A index. Now you say, depending on the K and the A index, you will know whether the ionosphere, now remember this, you have daily variations. You have, sorry, give me a minute. We said, although the sunspot cycle, whether it's on the high end or whatever, time of day, seasons, taking all that, those are very accurate, but still some approximate levels there. Those are guides. And things can change. Even during the high solar cycle, there can be complete days when you have about a 48 hours or 24-hour complete blackout of signals. When you say time of day, there's daylight. You're on the high end of the sunspot cycle. This is summer. But why is 21 megahertz gone, disappeared? Because we have solar flares. And the geomagnetic zones are disturbed, and signals start getting completely absorbed. And during such times, Then we have, now you say, if you look at the A and K index, you have quiet, 0. Then if you come down to 4, A index 4, you'll see it's quiet to unsettled. Then if you go down to 27 or 15, 27, geomagnetic activity is active. Those the magnetic zones, north and the south magnetic zones are active now, and signals going through those areas will start getting absorbed. Then we have 48 on the A index, minor storm. If you look at 208, severe major storm. 400, very major storm. So if you have a very major storm, you might have a complete blackout. It doesn't happen often, but it happens. Sometimes you switch on your radio and you find there's nothing. There's absolutely nothing. You wonder whether your antenna has been pulled out or whether there's something wrong with your radio. Maybe don't start thumping on the radio. If you know your propagation, you'll look at the internet and see, okay, is there a solar storm in progress? It's a very heavy one. Then what happens is, slowly the storm will ease and you'll start signals coming back to normal. So if you experience, that's we call a complete blackout, a solar blackout, ionospheric blackout, or solar storm, where signals get completely wiped out. But I want to, you see, most of these observations that we get are from more northern and southern stations. And what I mean is, all these experimental stations, the bulk of them are in Europe, North America, Japan, or maybe South in Australia, New Zealand maybe, and South Africa may be contributing. And so when we go through propagation, it's in a way, you know, I don't know whether to call it fascinating or very strange, that most of these theories and all those things are based in more northern, these European, American areas, and not so much on the tropical areas like Sri Lanka, southern India. If you go to Africa, Kenya, or Papua New Guinea, Indonesia, you know, maybe because our regions have been considered developing countries, we are struggling to come up, more or less. So we don't have so much of money to put into experimentation and all that. So remember this, I tell you, very often, if you are in countries in between the two tropics, close to the equator, very often you will find things that are a little different from what you find in the textbooks. What I have found is, if you take the Great Circle path, Taranga, do you think that we can quickly go on to the slides with the Great Circle map? One or two slides down. One more. Yeah, I think we had two maps at the end. One more. That the Mercator map, the flat R here. Let's look at this map. Now this map is a Great Circle map centered on Colombo. This is a computer projection. Now, you know, radio signals don't go on if you take a flat map on the wall, if you put a foot ruler or something like that, or a marker, and draw a line between 2 points, that is not the way the radio signals will go, unless you are in the tropics or whatever. Now see, look at this map. Now you have, at one point is Colombo, and the other point is the point exactly opposite on the other side of the world from Colombo. The antipodes, some people call antipodes, antipodes, that's the opposite point. And then back again here. So what happens is, during a solar flare or geomagnetic disturbance or a big blackout, what happens is the magnetic poles get so charged from the solar radiation, the extra radiation that happens during the solar storm, that signals start getting absorbed in the northern and the southern polar regions. So if you draw a line, we'll say up to about 30 degrees south and 30 degrees north. That's like countries covering the United Kingdom, maybe Italy, the Mediterranean area, right? And on the south, you see the map, you get Africa. Now, these regions will have a total blackout. Now, if you're in Sri Lanka, if you look at the map, see, equatorial, you can reach the point exactly opposite you, and then your signal going off again, that is sticking to this range between the tropics or the 30 and 30 line. So those ranges are not affected as much as the northern hemisphere signals and the southern hemisphere. And we are in a band close to the equator that is least affected. Of course, if the magnetic storm is very huge, you get a total blackout. But taking this possibility during a magnetic storm, when the band was completely dead, almost dead, I was able to communicate with a radio amateur in Cuba. I was able to do that because I was able to pick up broadcasting stations in the Caribbean. There was the Deutsche Welle relay station in Antigua, and I was hearing that. And also Brazil, Radio Brasilia. Now that's between this tropical zone. Magnetic storm in progress. BBC, European signals all wiped out. Radio Australia, Radio New Zealand, South Africa, all wiped out. The band is dead. But these regions were active. Unfortunately, there aren't that many radio amateurs in this region. But if you know your propagation, the moment this happens, you know, I have a chance now of long distance propagation with stations equatorial paths, not polar regions going north and going to America. If you want to go to North America, you'll see the lines, the propagation is going over Northern Europe. That will be completely blacked out. There's no chance. But the equatorial regions will yield signals, fascinating signals. When the band is dead, you're hearing them. So that again is, I'm trying to highlight to you the understanding of propagation. And we in the tropics, very often we have to discover these things because we are not told those things by the researchers who are more in the north and the southern hemisphere, the more developed countries, if you may like to name them. And we, the poorer, we have less money, less research done. And you as a radio amateur and myself as a radio amateur, we have to study that and bring that to the knowledge and the joy of radio amateurs in our region. Excuse me, I know there are some of our friends who are in the northern and southern regions. Excuse me for highlighting this range because I was talking about this, our tropical areas. In the same way, another thing, in 1983, I think, I experienced my first solar eclipse. Solar eclipse. Now that eclipse was across from the east to west, of course. It had a band affecting the total solar eclipse was in the northern, sort of north central India, extending to the Middle East during that daylight hour, because eclipse can be viewed only during daytime. I mean, I don't think I need to say that even, but a lunar eclipse you will see at night, a solar eclipse during the daytime. Now, coming back, this solar eclipse was going across, starting from about Singapore as sunrise came in, and then affecting a broad band across India into the Gulf, and disappeared when the sun set in the east and the sun started setting in on the west. But this whole thing lasted just 3 or 4 minutes. It was at 2:30 in the afternoon. And as I told you, the low frequencies almost get completely absorbed. There's nothing on the low frequencies during daytime. 2 o'clock in the afternoon, the solar, the eclipse was at, if I remember right, from about 2:38 to 2:42 in the afternoon in Sri Lanka. At that time, the medium wave band has only a few local stations, nothing from India. And on HF, nothing below the 4-5 megahertz area. And going on this theory, as I told you, at darkness, certain frequencies perform better. The low frequencies perform better. As daylight comes in, they disappear. So, taking that rule or that fact, what would happen during a solar eclipse? There is a temporary night condition or dark condition created due to this solar eclipse. So, as a radio amateur, I thought, well, at least for 2-3 minutes, we are creating night due to the solar eclipse. So, we should experience, even for this very short time, nighttime conditions. That was our hypothesis, maybe. Okay? During the eclipse, we should hear stations on the low frequencies that are not heard during daytime at that particular time, because now during the eclipse, we have an artificially created night. So, to do that, now there were scientists from America, from England, Australia, you name it. They all came to India because India was the best place to observe this, because the solar eclipse was across Hyderabad to Bombay, that strip. So they all took their tents or whatever, and they were waiting for the eclipse to monitor what the eclipse would be like and what would affect during it. And sadly, I tell you, nobody that I know of did any amateur radio or radio signal observation during the solar cycle, where the eclipse. Well, 3 days before, we started observing the band because there was no eclipse, but then you have to observe before, and then 3 days after the solar eclipse is over, so that you can really correlate your data. Well, to make it short, we waited, nothing on the other days. On the day of the eclipse, we had selected certain frequencies, like All India Radio was in Bhopal, Bombay, there were shortwave stations. In Burma, there's Myanmar, some medium wave stations and shortwave stations. And they were transmitting to their local audience, within 100 kilometers, not to Sri Lanka. And they were propagating because that was local propagation. Ground wave, you call it maybe. And as we approached the eclipse, we were scanning those frequencies. I was scanning from Piliandala and from Colombo, Dehivala, and my brother in Piliandala, Ron Forest7RO, we were monitoring these channels. Nothing happened. As we approached eclipse, 1 minute into the eclipse, we heard the buzzing, the beating of signals there. Suddenly the band, which had nothing, started coming alive. 1 minute into the equator, now darkness had set in over that area. Sri Lanka was in daylight, but we were bouncing signals, observing signals which bounce off the eclipse zone. 1 minute into the eclipse, we heard the buzzing of signal activity. 1 minute, a few seconds, say 15 seconds, we started hearing voice. And the eclipse was about 3 minutes. 2 minutes into it, signals boomed in, came up, and slowly disappeared. 3-4 minutes into it, absolutely nothing. Now, this is what a radio amateur with simple equipment. What did we have? An antenna, a receiver. At that time, I didn't have my ham license. But later on, we had another eclipse where we used the same principle and established communication. So what I'm trying to say, certainly, as Taranga said, some personal experiences in propagation. And I'm trying to tell you how you can get involved in this fascinating subject of radio propagation. It gives you another dimension so that you can enjoy. And also, in times of disaster, now we go back to the tsunami. At that time, we heard an announcement on the radio. There has been a tsunami or tidal waves, communications lost, people displaced. The government didn't know because there was no communications from the coastal areas right round, from Mullaitivu down to Panadura. And then didn't know what was happening. Announcing, if there's anybody, any organization which can come in, help us with disaster, food or anything. So we as radio amateurs, my good friend Kusal, he's there, I know, watching, 47 Kilo Echo, and Asanta, Dimutu, myself, Kamal, and we got together. I said, come on, this should be our finest hour for amateur radio. There is no communications from Hambantota, Tissa Maharama, at those areas. We don't know what is happening. The government had rushed in a satellite phone. After half an hour, the battery ran down. There was no electricity to charge it. Total blackout. So we on our own, we knew that we could establish communication. We knew our propagation. We had experimented. We knew that we can provide communication from the south to Colombo. So we were getting ready. Kusal, Asanta, Dimutu, and a friend of ours, I think you would have read that report, so I won't go into details. But what I say is, we were preparing to go because it was impossible to reach the Prime Minister's phone. 3 lines completely saturated. We sent a courier. Bharat, our good friend 406 ABC, Bharat undertook that mission to inform the Prime Minister that if they needed our help in communication, that we were prepared. And we didn't wait for him. We were getting ready to go. Then we were going to leave at 12 midnight. 11:30, we get a call from the Prime Minister's office. You have got this message that you can provide communication. Can you? There's nothing there. No electricity, no fuel. Total destruction. But you say you can? I said, yes, we can. Yes, we can. So, because we knew we could. And then he said, yes. What do you require? I said, we require one thing. Your blessings. If you are stopped by the police or the military, Sri Lanka was in a state of civil war, more or less, to say that we are on a mission with the blessings of the Prime Minister of Sri Lanka. And his secretary gave me, I was the president of the Radio Society at that time, and we were coordinating with this group of friends there, and he gave the Prime Minister's personal mobile phone number and his number. Said, do not disclose this to anybody else. In an emergency, you're free to call. And that confidence that we could go and set up communications is because we were radio amateurs and we had studied, taken that interest. My friends, Kusal, Dimutu, and Asanta reached Hambantota. We were going to Tissa, but we were, Prime Minister Rajapaksa wanted us to go to Hambantota. About 10,000 feared dead there. So they got there through the country, difficult terrain or whatever, 4-wheel drive, got there. 7 o'clock they were there. 7:22, if I remember, they started transmitting signals. This is Forest 7 RS from Hambantota, disaster communications. Do you hear? And we said, yes, we hear. And we were at the Prime Minister's disaster room receiving those signals. And there were so many of our radio amateurs waiting with their better antennas. We were portable. Better antennas, listening They didn't disturb in case we wanted a relay. So what I'm saying is we knew that we could go and establish communication because we knew the art of communications using our propagation. We knew we could do that. So let's come to the next topic. Then modes of propagation. We have sporadic E. Now we have the D layer, we said, which absorbs signals during the daytime. And then we have the E layer, which is a day area. It also absorbs signals, but not to the extent that the D layer almost completely takes it away. Now, the E layer, during the day, during certain times of the year, we can communicate for short times using E layers. Forget about the F layer above, which is the main high frequency communication level. Now, the E layer, during certain times of the day or year, depending on the years, sunspot, solar, and all that cycle, you get sporadic E. Sporadic means not all the time, no? Occasionally, short bursts. You get E clouds. And if we are alert, we can bounce our signal off the cloud and get it back to our next location. Sometimes it also bounces from one cloud to another and receives much longer distance on lower frequencies than possible at other times. So that is why you call it sporadic E propagation. Then you have scattered signals. Now you have, when the signal strikes the ionosphere, the signal is not a pencil line, like, hits and comes back. At the ionosphere, the signal, when it hits the ionosphere, the signal can get scattered. The main beam will be refracted back to Earth, but there is some scattering out there. I mean, just imagine fireworks. You send out a fire, what do you call it? Fireworks, cracker or whatever, up into the sky. When it hits there, what happens? You get sparks flying in all directions. Similar, something like that. When it hits the ionosphere or even the E clouds, there is some power which scatters, and you get scattered signals. Now, when I beam my signal from Colombo to India, what happens is somewhere between the 2 points, it hits the ionosphere. And at that point, what happens is there is some power, energy, my signal, which also gets scattered backwards, backscatter. We call it backscatter. So now we studied, or we looked at the zone, the skip zone, that depending on the frequency I select to reach, we'll say Delhi, New Delhi, India. My signal will reach India, but on the way there is the skip zone, the dead zone. But when the signal hits the ionosphere, there will be a certain amount of energy that will be sent back or side. So all at that time, we can hear this signal, although the main signal is not heard. So that way, you have to experience that. Anyway, that is the scattering of the signal in the ionosphere. As I said, it doesn't strike the ionosphere like a pencil line and go, so that nobody else, anywhere else. No, when I transmit to India, I'll be heard even if the conditions are okay. I'll be heard in Kenya. I'll be heard in Rangoon or Yangon. But my primary signal will be there, and my scattered signal will come back. Now see, at that time, why my dead zone is because the distance between Colombo and New Delhi. But the ionosphere strike, the point is halfway between. So from that point, signals are sent back in all directions. So some power I will receive even in the dead zone. Those signals will not be as strong as the main signal that hits New Delhi, but somewhere even in Jaffna or in southern like Trivandrum, the signal could be heard. That's how on 40 meters, sometimes at about 5 o'clock in the afternoon or 6 o'clock in the evening, when we communicate with Bombay, we find that signals in the southern area like Chennai, Calicut, those areas, we lose propagation. But all of a sudden, we hear a little bit, something like a fluttery signal. Now, those are the scattered signals that we hear. Okay, then, yeah, the slide has here, occurs 100 kilometers altitude. This is the solar E propagation. I think self-explanatory. You can go through that. We've been almost 1.5 hours into it. I want to wind up by about 9 o'clock. So it's, let me see, occurs at 1,000 kilometers altitude. I'm sure you can look at the picture there, and that's understandable. Appears as thin, localized clouds. The diagram shows you. And lasts from minutes to hours. Yes, because these are sporadic. I said, I mean, the conditions, we really don't know why we can't say this is why it happens, but it happens. And so these sporadic E clouds happen. And if there are people who are DXing purely, their main aim is to E cloud DXing. They are not interested in high frequencies, the F regions. They are, because these happen rarely or not as often, sometimes unpredictable, but radio amateurs who have studied propagation know the likelihood are during summer months, during high solar activity. So you see, this whole thing is a science. It is not just passing the exam, getting an amateur radio license, sitting in front of this and say, CQ, CQ, CQ. This is, no, that CQ has to be scientifically programmed, understood, and sent out. So that the signal you get back, you understand how it happens, why it happens, and you have planned it. I'll give you another example, personal example. There is a small radio station which is called CHU. This is a Canadian time signal station, like WWVH and WWV or JJY. Now, this Canadian time frequency signal station operates on various frequencies. They have something like 17 megahertz and also down at 8 megahertz and one at 3330, 3 megahertz. Now that is the hardest to hear because of propagation. As I told you, those low frequencies need darkness between the transmitter and the receiving point. And that happens because Canada is so far away. It's almost 11 hours between our sunrise and sunset. We have what you call a small window. In amateur jargon, we say we have a small window. That is when it is possible to hear this station. So, making some calculations and all that, this station operates 3 kilowatts. 3 kilowatts is like 3 watts on ham radio. Very low power. It's not for worldwide, it's for the Canadian area. Time, it gives the time every minute and the frequency so that you can tune your electronic equipment or your clock or whatever. So these come down from pre-internet days. So to hear this station was my ambition. Low power, far away in Canada, how to pick it up. We had after calculating, realized at about 5:50, between 5:50 in the morning and about 6:05, we have a small window of 10 minutes or 12 minutes when it is reaching sunset in Canada and it is sunrise. That's the only time that we have total darkness between Sri Lanka and Canada. Calculating it, and also the time of year, and then you get the gray line. We come to the gray line. when the propagation is maximum or the best. And waiting new January, late January is the time that all these factors would fit in, like a hunter, with a camera. I don't like killing animals. In our Sri Lankan culture, we photograph. So like a wildlife photographer, waiting, hiding at the water hole, knowing that on a moonlit night, there won't be animals coming. That at this time of the day, year and all that, and he waits for his prize target, the leopard, the Sri Lankan leopard, to take that prized photograph. And he waits, and he waits, and he knows it could be now. And he fine-tunes his lens, and he waits for that picture. So it's something akin to that. If you plan your DX, how to do it, when to do it, what frequency, is not rocket science if you study properly, right? Now we talked about scattering. Tropospheric scattering occurs. Okay, backscatter propagation, we spoke about that. Signal sounds similar to scatter mode. So please go through this. We're trying to say, I think, I don't think I need to expand and that. But
Yeah. Maybe you can go to the next slide.
Yeah, okay. Can I skip backscatter? Yeah. Tropospheric propagation. 3 key factors.
By the way, Victor, sorry.
Yeah.
If our viewers have any questions, they can raise their hands so that we can take them in. And at the end of the slideshow also, we can have questions. So
okay,
we can quickly go through the slides.
Okay. Taranga, I'm concentrating on the main slide and talking. I might not see a hand raised, right? I might not know. So please feel free to break in and say, Victor, there's a question or something, okay? And if I can answer, I'll be happy to answer. Otherwise, I'll tell you, you'll have to refer to a more knowledgeable person. Okay, we're going on.
Victor, hold on, please. I think Ravi has a question for a 6 Romeo Alpha Victor.
Yeah, Ravi. Yes, go ahead, Ravi. Ravi? Taranga, are you hearing Ravi?
Victor seems like he's dropped. So yeah, go ahead, please.
Okay. Enhance tropospheric refraction.
Excuse me, Taranga. I think Mr. Ravi has his question on the chat.
Yeah, am I audible? Please? Am I audible?
Microphone is on mute, I suppose.
Am I audible now?
Yes,
Hello?
we can.
Ravi, you're coming through fine. Go ahead.
Thank you very much indeed, Victor, for your explanation. Very much informative for me and as well as for others as well, I believe. Taranga, I have put a question on the chat. My question was regarding the long delayed echoes. I wonder whether you can see there. What I want to know is, I heard about the long delayed echoes, right? I did some search in the internet also, but I wanted to know whether will it occur at any frequency, any time of the day?
Victor?
I think Victor's microphone is on mute.
Right. Now it's okay. Right? Sorry. I had touched the keypad, I think, inadvertently. Right. Okay. You're hearing me okay, Aruna? Ravi?
Yes. Now it's loud and clear.
Right.
Loud and clear.
How do you hear an echo? Echo happens if the voice, or even if in a CW signal, you have 2 signals. One a little ahead, or maybe a slight delay, so that you hear 2 signals. Wow, like. Now, in high frequencies, what happens is you can have multi path propagation. Now, if the ionospheric conditions are good, you can have not a single, that is, okay, from Colombo, one signal might hit over India, another one maybe a few kilometers away, and your signal might come as an echo, but so that one is a fraction of a second delayed. Okay, so that you will hear at some time of the day, because depending on propagation. Now, the same signal, we'll say, take for instance a broadcast signal. Now, a listener in India might hear an echo. We'll say you're listening to the BBC. You say London, like, you get the. But at the same time, that same signal, somebody in a different part of the world hearing it will not hear the echo, because for him, the propagation will not favor multipath. Okay? That's number one thing. Then there is the other thing where you get long path and short path. When propagation is ideal for both long and short path, one signal will be, we'll say, 10,000 kilometers. The other one will go round and come to you. There will be something like a half a second or a little less delay. I have heard it many times, especially you hear it on 15 or 14 megahertz, or ideally on the broadcast band, BBC and Radio Australia. Those days, at about 6 o'clock in the morning, when the propagation during the time of the year, when both long path, the signal from Melbourne, Shepparton rather, transmitting station, would reach Sri Lanka on the short path on 15 megahertz or 19 meter band, and at the same time, the signal would go around the world and come. It doesn't happen all the time. It can happen for 10, 15 minutes, sometimes 30 seconds, 30 minutes, and then disappear. The signal at times would reach very high levels where both the echo, the short and the long path signal would come, interfere with each other. The echo will be so bad that you might not be, it'll be wow, 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 wow sort of thing, that you might not hear it. So that's two things. And another way that it can happen is that we have noticed in the broadcasting field, there are times when, for instance, the BBC or the Voice of America, they are programming originating in the Washington studios or London studios, and they are sent to a relay station in the Far East those days, or to the Philippines from the Voice of America. And there were the same transmitting station was used in another part of the world, because the main target area was Southeast Asia. So that same frequency could be used in Europe, for instance, to cover a European area where that signal will not be heard in that target area. But due to very, I wouldn't say free, but rare occasions, or maybe, use the term freak, or rare occasions, a listener in Sri Lanka would hear both the Philippine station and the station in Europe carrying the same program, the World Service, or the Voice of America English service to Europe and the Far East. And one is closer and one is fed with a satellite, because satellite, the satellite delay on your phones, you have the satellite delay. When you're talking at times, you get the echo. Similarly, that satellite fed signal in the Philippines, which is relayed, will be a fraction of a second delayed compared to the signal coming from England, from London, from Daventry. So then you can also have the echo effect. Now, there may be other instances that you can hear the echo. Ravi, I need to go into it a little more detail and pick up. These are the three things that come to my mind in a flash, but if I go through the system and study a little more, I might be able to come up with some. But these are three instances I want to explain to you were most common. Okay? Would that answer your
Thank you
question,
very
Ravi?
much, Victor. Yeah,
Okay.
thank you very much, Victor. And Taranga, thanks very much for letting me in.
Thanks, Ravi.
You can go ahead
Okay.
with the
You're
presentation.
welcome, Ravi. Thank you very much for listening. Taking
Naina,
an
maybe we
interest.
can go to the next slide.
Yeah.
The tropospheric ducting is
Yes,
important.
tropospheric ducting. Now, this is very interesting. Tropospheric ducting, usually we encounter this in VHF and UHF flag, right? Now, as the term ducting refers, or it's something like being trapped. Then, between layers, you can get your signal like trapped and carry through. Now, we know your signal. Now, I don't know which slide is vertical. Okay, sorry. Now, you see two layers. Now, the signal is bouncing. I think not this slide.
Naina, go to the 34th slide. Next one.
Not this one. The other one, let's see. Is that the one? Is it clear
Yes,
enough?
ducting.
Yeah, okay. Now, the signal can, now we'll see, what's happening is, it doesn't come down to the earth, but it is bouncing between layers. So that sometimes, now I'll give you an example of this, which happens with signals between Sri Lanka. Well, I'm taking Sri Lankan examples because that's what I have done and what I know. And communicating with stations in North America on HF. Now, we start communicating with European signals, the Delta Limas, the Hotel Bravos, the Italian stations. They are 5, 9. You are in a pile-up. And as the night progresses, what happens is this pile-up gets less and less, and the European propagation starts fading. And all of a sudden, what happens is the signals in the east coast of North America start coming in. And I can hear New York, or maybe in Canada, Halifax, or Prince Edward Island coming through, and I hear the European signals very weak, whereas Europe should be much stronger, but it has faded. And this is what, one of the Voice of America engineers, who was an American who was in Sri Lanka, as you know, the VOA station in Colombo, now it has closed up. They found that there are signals that this was happening, that there was something like a tunneling effect going through. Our signals were tunneling through Europe and reaching North America. But the European signals were very weak, something like a scattered signal. So the European signals were scattering in the ionosphere and coming back to us as very weak fluttering signals, whereas in theory, we should have heard them loud, but the North American, the Canadian, East Coast Canadians and East Coast North American signals were coming. The Victor echoes, the Victor echo 1, 2, 3s, the Whiskey 1, 2, they were booming in, while we heard very little from Europe. So it was obviously our signals were tunneling through the layers, maybe the F1 and F2 layers, and reaching North America. So, as I said again, we have to theorize. We have to assume, taking, of course, not wild theories, but taking a lot of data and build a hypothesis that this could be because of that. So that is HF ducting that we have come across. Then also on the VHF mode, we have, and also it can happen during aurora. During the auroral, so when aurora is experienced in the northern hemisphere, we'll say, yeah, it also happens in the southern hemisphere. But since most communications go Europe, North America, and Asia, we have been observing that more than the southern signals. But if we concentrate on the southern hemisphere, I'm sure we will also observe that. So what happens is, during the aurora, those regions, again, something like these what do you call this, eclipse, it creates an artificial, temporary, ionospheric abnormally muralis. And at that time, certain signals could go through ducting within those areas and also beyond. So these are areas that I think we cannot cover in just a few seconds or minutes, but may be aware of it. So solar particles interact with the Earth's magnetic field. That's in how the aurora takes place. So I'm sure there is enough material that you can hear. Okay, there's a lovely diagram here, how the ducting.
Victor, we have a question from Aruna.
From?
Victor, it's for me. Yeah. Is it okay to ask now?
Yes, go ahead, Aruna.
Victor, have you experienced this ducting effect, tunneling effect for our in-country VHF communication also?
Yes.
Have you experienced in that?
Yes. Shall I? I was going to come to it, Aruna. VHF. Now, what happens is, sometimes, now, over the last so many years, we have observed the VHF signals. And we know that during February to early April, we start hearing Indian stations on the VHF, on our repeaters. And also, at times, direct signals, from Hyderabad. I think long distance I've been like Hyderabad or this Visakhapatnam, Vizag, and also Calicut. They have heard from one station to the other. So there has been because that's the time when we have the sun close to the equator. So then we have this equatorial ducting effect because of the effect of the equator. When the sun is in the northern hemisphere, going to the northern hemisphere, or again in September, November, we have this suddenly we hear the VHF signals. Of course, repeater signals are more often heard because of the height at Pidrutalagala and all that. But from our own homes, using just 20 watts, 25 watts, maybe a beam. I mean, nothing very fancy. Most of I think Jali has done some fantastic VHF long distance DXing. And also this period where this VHF contest, hilltop contest, has also been selected, taking this high, possibility of ducting and this interlayer propagation. So that's one thing, because of the effect of the sun during the movement of the sun to the northern hemisphere, or coming down during summer and winter, we have been noticing these two conditions. So the thing is, we have to assume, because we cannot go into the ionosphere and make any, but we have to take observations. And also, as the picture shows, some signals being sent to the ionosphere and taking measurements. And we have determined that there is ducting taking place. Now, your direct question was VHF. And another way that is very pronounced is, of course, within Sri Lanka, as you say. Within Sri Lanka, now look out for the next 2 months. Now we are going into the dry spell. The northeast monsoon is slowly fizzling out. By end of January, it will be over. And the other monsoon, southeast monsoon, will come in May. During this intermonsoonal period, we have very hot weather. And when we have very hot weather, we'll say in February, March, what happens is the earth, the surface of the earth, just imagine, say like Colombo or whatever, or where you are, Aruna, it's very hot because the ground is being heated up by this very heavy sun. And as we go up elevation, it cools. But what happens is, suddenly we have a shower of rain. Now, the rain clouds are not 200 kilometers up. The rain clouds are much lower than the ionosphere. So what happens is, when it rains, suddenly the surface of the earth gets chilled or cool. Suddenly the temperature drops, and say 50-60 kilometers up above the rain clouds, it's that temperature is maintained. We'll say at 4 o'clock in the afternoon or 2 o'clock in the afternoon, the temperature on the surface of the earth and Colombo or Sri Lanka or wherever is we'll say 20 degrees, and as you go over, it has gone up to like 15 or 10 degrees. Suddenly what happens is there's a shower of rain, and then the temperature on the surface gets colder. And then what happens is we have what you call a temperature inversion, right? Where on the surface of the earth, for a short time, it's cooler than maybe 50 kilometers higher. It's a temporary thing because of and that at that time, we have ducting taking place. So one of the reasons why ionospheric ducting takes place, you will see, is temperature inversions, right? Above ground sea level, you say surface ducting, then elevated ducts forms between 450 to 200 meters above ground, created by double discontinuity in refractive index. See, so you see, now I will not go into very detailed into that about but what happens is there is something like a temperature inversion or ionospheric inversion because of the situation that is created by rain or high humidity, so that the signals naturally, the VHF and UHF signals especially, are affected by the heat and all that. Now, you see, we made similar observations when we had a repeater in Colombo at the OTS tower in Piliangala. We had a vertical Slim Jim. That was the easiest antenna to put. We had a Slim Jim, and we had a VHF radio, and we were observing the signals. Now, our common belief those days, I wouldn't say scientifically, but in the common belief among radio hams is, line of sight is not affected by the time of day. But it was not so. The repeater, which was 5-9 at 6 o'clock in the morning, as the sun, by the way, for anybody listening who is not familiar, it was about 25 kilometers, a short distance. And as the sun rose, the signal started dropping. And at noon, at 2 o'clock, the VHF signal at 6 o'clock, 7 o'clock in the morning, which was a complete deflection of 5-9, other side, dropped down to 5-7, 5-8. And what could affect other than the local conditions of day and night? Rain, yes, at times when it rains. Now, these are things that you should observe and bring out, because scientific observation did not stop 50 years ago or 100 years ago. It is something which is evolving. We are discovering, and you may be the guy who will discover that, put it into a theory, taking data and also the theories of propagation and all that, and come up with a theory and prove it. Prove your hypotheses. And so that is what, Aruna, I don't know whether I stuck to your question or deviated from it, but do you see what I meant about the ducting effect and how we experienced that in Sri Lanka?
Thank you so much, Victor. I got a very practical explanation from you.
Okay, thank you.
I think your experience gave me a lot of information. Thank you so much.
Now, my experience is what I observed in the last 35, 40 years as a radio amateur. And what I had to pick up was from the experiments, from the knowledge of those people before me, who are our peers, our mentors. Now, today I'm talking to you about my experiences, and I hope, I'm sure you will propel that as the future and pick up on that, develop on that, and let us know. As I said, in Sri Lanka, South India, and in the tropics, there is very little being done on HF and VHF propagation. Very often people talk about VHF propagation as a local means of communication. I visited a friend of mine in Switzerland in 1983. I had just got my license, and he was, what's his name? I call sign now, HB9QQ. HB9QQ. He was Europe's one of fantastic VHF DXs. So my friend took him up to his place and he said, let's go to my shack. It was on a mountain top. And at the top of the mountain was his VHF antenna stacked arrays. And we had to go down like a space capsule into the mountain, like a nice dome, waterproof. And there was his shack, like inside a space capsule. And I asked him, I had a small VHF transmitter, a Kenwood TR-2300. I think the maximum power was 2 watts or so. I asked him, he was, Peter. I said, Peter, how far have you worked VHF? He said, yes, that's my passion. I have contacted South Africa. South Africa? I said, South Africa? I said, have I got? I said, no, Victor, not with 3 watts. You need something like a stacked antenna and maybe 500 watts or so. And he says, my dream is to contact Australia. He had done many transatlantic, that is across the Atlantic to North America and all that. So what I say is, we have to do our experiments and come up with theories for Sri Lanka and the tropics. Okay, so then Taranga, are we going past our time?
Actually, we are.
Yeah.
But Victor, I think we are coming to the very tail end of
Yeah.
the syllabas. So
Yeah.
let's quickly run through these angles and
Yes.
then some NVIS theories, and then that's it. And some gray line propagation. Yeah. With that, we can come to the end.
Okay, we'll do that quickly. Okay, I lost the slide there, Taranga.
Oops, I think I lost my internet connection. Just give me a second.
Okay.
All right.
I'll see. You have to excuse me. Sometimes I go into too many details. I hope I didn't. That's what happens when you are a teacher or a lecturer, you know. And also, you're talking to a broad audience. Okay, right. Frequency and incidence angle. Okay, now you see what happens is, okay, we have, okay, we'll take this because for the exam, my friends, local friend, you say maximum usable frequency, MUF. Say maximum usable frequency between 2 points. So that is determined by, of course, ionospheric sounding stations and all that, taking the, so you have, and all these research stations and all that, they will have charts for you. So the maximum usable frequency, depending on the ionosphere, see, as I said, between London and Colombo. Sorry. I hope I'm not losing my voice. So, we can determine the maximum usable frequency. For instance, we'll say at this time, the maximum usable frequency is, we say 14.2 megahertz. So that anything above that will strike the ionosphere and go through. It will not be refracted or bent back towards the earth. So the frequency, the maximum frequency at any given time between 2 locations is called the MUF. Then, in the same way, we have the lowest frequency. Why lowest? Because of absorption, the delay at one point. There will be frequencies which are not possible to communicate because they are absorbed. So on one side, you have the signals penetrating, going through the ionosphere and not coming back. That is the maximum usable frequency, MUF. Then you have the lowest usable frequency, because as you come down in frequency, depending on the time of day, your signal will get lost, not high enough to get bounced back. So one signal might go through the ionosphere and the other one get lost in the D layer and all that and not refracted. So LUF. And in between, you get a frequency, we call it the OWF, optimum frequency, right, that you can use. That is, now if you use the MUF, that is the highest possible. And you know, the ionosphere has variations. So at this moment, 14.2 megahertz might go through. But due to sudden differences, 14.2 might drop to 14. So the maximum, if you are using the maximum usable frequency, at times your signal might get lost, right? OWF, optimum working. So what radio amateurs or more broadcasting stations, you know, broadcasting stations, they have to provide a reliable signal to normal average listeners with a radio, not communication receivers, transceivers with beam antennas. So they have to determine what the most reliable frequency would be, not the maximum usable. So that would be the best frequency, a little lower than the maximum frequency. And that we call the OWF, optimum frequency. Some, of course, use French terms, OWF, and optimum frequency of, something like the UTC and all that. So OWF, optimum working frequency. So if you asked a question, by the way, what is the best frequency? Would you use the maximum usable frequency, optimum, or OWF? They might not, in your question, they might not say optimum working frequency. They say OWF. Between London and Colombo, would you use OWF frequencies in the OWF region, or MUF or LUF? Then you know optimum, most reliable will be just a little bit below the maximum usable frequency. Okay, then can we go on to the next ones? These slides are
yes, Victor, I changed the slide, but it's not refreshed yet. Just give it a second.
Okay, so as I said, long distance communication depends on the ionospheric condition, not really between the first hop, the second hop. Now between Colombo and India, there are lots of possibilities for us to communicate. But the next hop, when you go to the Gulf or something like Cyprus or Egypt, then we have another spot hitting, over the Gulf maybe. And then a third hop hitting, and then the conditions of the ionosphere are different. So more or less, we have to take an average. Okay? Between Colombo and Delhi, the MUF might be, we'll say 20 megahertz. But at the next stop, because it's less ionized, it might drop down to from 20 to something like 18. And at the next hop, it might drop down to 14. So we have to come to an area where we can use a frequency that's heard best in our target. Now, in between, sometimes when we are communicating with a station in England, an Indian station is listening, and I lose propagation with the British station because my MUF or OAWF has dropped now. But between that point, but between India, my frequency is still close to the OWF, or it's even better. So sometimes I might get a relay. My friend in India will say, Victor, he wants to sign off, he's losing you. And he is listening to both of you. Okay, now next, there's a much talked about topic in recent times. Okay, I lost the slide. Let's see. Near vertical incidence skywave. Right, now we spoke about the angle. If you now just imagine, just to take get an idea, if you go near the river, a lake, you take a stone and you hit. If you hit low angle, it might skip and go 3 or 4 hops, we'll say, ionospheric hops. But if you hit it straight down, what happens? It will just not get bounced back. So our ionospheric bouncing is also in the same way, depending on the angle of our signal going out to the ionosphere, my signal might come down or go through. Now in the morning, a classic example I would say, in the morning, we Sri Lankans, we communicate on 7 megahertz, 7060. Now, I don't hear my friend in Kurunegala, which is 50-60 kilometers away, or I don't hear somebody in Aturugiriya, like Christy. I think Christy is there. Hi, Christy. Christy's signal is weak, fluttery, because the angle between Christy, who is about 30 kilometers away, and my QT8 is almost a clear vertical angle, which at that time, 7 o'clock, 7:30 in the morning, the ionization is not strong enough for this sharp angled signal to get refracted. It will go through. Some of it will get scattered and come down. So his signal will be fluttery. Whereas somebody in Calicut or Chennai or Trivandrum will come blasting in. Now he's about, say, 800 kilometers away, because the angle of refraction or the incidence angle is much sharper. So like that stone that you hit onto the water with a low angle, similarly, you will find that when you go to the Charminar net or Belgaum net, 7055, oh, the Indians are blasting in, and 7080 blasting in. I copy good old Money, who's been shouting away so many years now as net controller, blasting in, and he'll say, your signal is 59 in Alleppey, whereas somebody 30 kilometers away, I hardly hear him, because he is in that skip zone and his angle of refraction is too sharp. Now, taking that into account, we come to this situation where we need emergency communications. Now, but short distance. So then what do? Our signal will be sharp. The angle will be sharp anyway. We can't vary the angle because we can't have an Indian station relaying back to Kurunegala or Aturugiriya. So we have to find a way of getting our vertical incidence, the signal, skywave signal, down to Earth, because that person is in that skip zone. So my signal, the ground wave has stopped and the sky wave is too sharp for it to come down there. So then what do? We'll say, well, look at the slide. Radio waves transmitted nearly vertical to ionosphere, 60 to 90 degree angles. Signals reflect back down, covering circular area of 400 kilometer radius. Eliminate skip zones common in traditional HF communication, effective for regional communications despite terrain. Now, you see, now you will get the idea that if you use this near vertical incidence skywave theory, that you can communicate magically at short distances, skipping the zone and all that. No, in theory, yes. But what happens is, at any time of the day, now you see the first one, optimal frequency is most effective 2 to 10 megahertz. Now, at 7:30 in the morning, whatever angle you use, you will have a skip zone. Whether you are sending vertical or lower level, you can have a low angle antenna where the signal is almost sent vertical. If you have a sharp angle or something like a beam, then the angle of transmitting will be much less than a near vertical. But you are sending your signal near vertical because you want to cover short distances. Then you have a low level antenna, or as the picture shows now, you see these whips and all that, they send out, they are not beams, they are signals which radiate at very low, very sharp angles, sorry, not low, sharp angles to the ionosphere, near vertical. Then what happens is, if you want to use near vertical skywave propagation, the most important thing is to determine at the time you want to communicate what frequency you have to use. Because you have to use vertical because that is the short distance that you have to cover. You can't use beams and sophisticated antennas. They are not of any use because you need to beam up and get the signal down. Then what is the frequency that will bring this vertical signal down to you? And that is determined by the time of day, and that frequency range will be between 2 and 10 megahertz as the theory is. So for near vertical incidence propagation, skywave, or emergency communication to cover short distances, you have to use low-level antennas which will give you a signal, a vertical, not a beam, a vertical, something like a whip. Or if you're using a dipole, a very low. You know, a dipole, as you go from ground, as you go higher, the angle of radiation comes down from vertical, near vertical, down to, so if you have a dipole at about 100 feet, the angle of the thing will not be vertical. It will be, of course, some signals will go vertical anyway. But what I say is, if you're concentrating on emergency communications using NVIS, there are particular type of antennas which will make sure that your signal goes up. But remember, beaming vertical is your requirement, but that signal which will be refracted back to Earth will depend on the ionospheric conditions. If the ionosphere will not reflect back 7 megahertz at 8 o'clock in the morning, it's too low, then you have to go to 3 megahertz. And then your vertical signal will come back. That is why we say you have to depend between 2 and 10 megahertz. Maybe in the afternoon, maybe at 9 o'clock or 10 o'clock, 7 megahertz is too low. 3 megahertz is completely out because D layer comes in and squashes the signal. You have to go higher. And then what happens is, that is where you have to experiment and see where your signal will come down. Read more on that. Unfortunately, I can't cover too much or maybe one day we'll take that as a matter of interest and concentrate 100% on every aspect of NVIS. Okay, then multiple hop propagation, we are coming to that, occurs when radio signals reflect between Earth. I think we have dealt with that. Distance covered by the signal in one ionospheric hop, yes, up to about 3,500 to 4,200 kilometers. You so determine if you are going to contact somebody in Australia, in Melbourne, take the distance and see how many hops it will happen. And if you are using a low-strung dipole, your signal is taking almost vertical, and that has to have 10 hops, which will mean your power is not enough. That's why when somebody is using a dipole, at the same time, same power, maybe somebody is using 100 watts. I use 100 watts, and we are connecting onto somebody in Melbourne. Same time, same frequency, ionosphere is the same. But why is the guy with a dipole not reaching Melbourne with the same strength as my signal or somebody else's signal with a beam? Because with a beam, his angle of taking off will be much lower. So he'll do that distance in 3 hops, whereas a lower strung dipole, almost vertical, will take 10 hops, and every hop will lose power. Okay? Taranga, did you want to say something?
Negative,
Okay.
Victor.
Okay, then we come on to long path and short path. I think I touched on that when I spoke about Ravi. Ravi, I told you about the echo, that any 2 points between, we'll say, Colombo and London, there is a short path that is going over the Middle East. And if you look at the Great Circle map, you know, take a globe and put a pin on Colombo. Yes, as we say Colombo, you say Colombo, and you'll say New York on the extreme end. And the signal on the other way. Oh, see, now here you are, the gray, long and the short path. The short path to, say, Canada, northern Canada, we'll say that point, Newfoundland. Now, Sri Lanka, Newfoundland, the short path is going over Lake Baikal and almost southern Sweden and slanting down and reaching Canada. What is the long path? The signal goes down Australia, below Australia, New Zealand, almost deep South Pacific. Now this is the beam heading that we are using for Jalia, who is halfway in that South Pacific, a little down. And then the signal goes past the point directly opposite Sri Lanka, which is the island of Galapagos in the, say, west of South America, and goes to Canada. Now that is the long path, as if touching your ear, short, and going around your neck. So that's the long and the short path. So there are times of day when the short path will not propagate on a particular frequency because that frequency may be too low while going round, because they say there's daylight on one path, more daylight, but on the other path, although it is going through night time, and so sometimes the long path becomes better than the short path. And then we'll come, I think, to the final one, gray line propagation. What do you mean by the gray line propagation? Gray line is, you get the terminator. Now in this map, if you look at this map, you get the terminator. The terminator is the line between day and night. So you get the day, night, due to, now this will change from the time of year. Now, if you take now this map, I think looking at it seems to be during summer. During summer, because Europe is a lot of day. Now, if you invert that, of course, the time of the year, the gray line will change. I don't know, Taranga, whether you have another map for the gray line at other times of the year. Anyhow.
Unfortunately, no.
No, okay, no. We'll stick to that. Maybe we can expand on gray line sometimes as a matter of interest, but we get back to that map and we'll stick to this example. Now you see somebody in Eastern Australia, maybe we'll say like Brisbane. Is it Brisbane? Yeah, Brisbane is in Queensland, right? Brisbane. Now, see, his terminator, day, night, is going north and coming down to South America. We say somebody in Brazil. Now, his signal also, if you take the great circle path, this gray line between two locations does not happen every day. It varies, it changes. Now, if you take the, say, now this may be December, we'll say it's July. I mean, it'll take time for me to calculate and tell you exactly. So let me not try to say, okay, I know this, that, I know. Oh, gray line this month. Another 4 months later, this terminator will change. And sometimes it might not be this curve. It might be like a box shape, right? Terminator. Because day and night both equal when the sun is over the equator. Now, at this point, Brisbane and Brazil are on this terminator line. And if you look at his propagation line, beam heading, at this time of the year, it so happens that his beam heading, his radio signal to reach Brazil will take this path, right? So that at this time of the year, I told you about my Canadian experience, why it happened. So similarly, now this gray line between sunset and darkness, for him, this day, Brisbane to Brazil, if we use sense his signal, this will be the best possible way that he can contact Brazil. But then there's another aspect. So the propagation is best at this time of the year when he has the gray line, and the gray line also corresponds to his radio signal, the beam heading or the radio signal that will propagate, because the radio signals don't bounce here and there. It will more or less take like a straight line, a great circle path. So what happens is the great circle path between Brisbane and Brazil on this day, or maybe for about a week or so, because of the movement of the sun is not every day changing slightly, will correspond to his great circle path. And that will be the time that will be best for him to communicate with Brazil from Australia, or the other way around. But there's another thing. Taking the time of year of the sunspot cycle, although the terminator is the same, the year sunspot cycle might determine whether the same amount of ionization is present on this path during the height of the sunspot cycle and the lower cycle. But the gray line will remain the same, but the solar cycle will change. So we'll say take at the height of the solar cycle, because there is so much ionization, he can use high frequencies, maybe 21 megahertz or even 28 megahertz to communicate with Brazil, right? However, during the low sunspot cycle, through great circle path and the gray line corresponding to each other, you get the best time. However, your frequency band will have to change. So during the low sunspot cycle, if you are going to use gray line, you might have to use 7 megahertz. And that will give you the best signal between these two locations, which hug the gray line and the great circle path. But during the height of the sunspot cycle, again, it will be a higher frequency, but the best path to observe. So I don't think I can explain that in 5 minutes, great circle paths and all that. But remember, the gray line has to correspond with the great circle path. When it corresponds, that is the time for the best propagation between two locations. Okay? Then you have these maps. These maps are very useful. If you want to calculate the direction or the distance between 2 points from your location, you have to use a great circle path centered on your location. In Colombo, now this map, great circle map of Sri Lanka. Yes, this is centered on Colombo. Now, if you take a foot ruler or something ruler and keep it from Colombo to any point, that will be the direction your radio signal will go and has to follow. You have to beam. And at the same time, remember, the other way around is the long and the short distance is the short path. And you have to determine when the bands are good to use whatever, but your direction will remain the same. And also, you can calculate the distance. Some of these maps will have circles around, like the map I showed you, which is what I got generated, that dark flat map with lines. That gives you, I can share that map with anybody. I think it's already shared. You can determine the direction, and also there are the dotted lines which indicate 1,000 kilometers per circle. So that between Colombo and Melbourne, if you count the amount of dotted circles, if it is 10, you will know it's 10,000 kilometers or 5. So that way you know the distance, and when you know the distance, here, if you take this, you might see the dotted lines there. So between Australia, I think you get about, here you get the marker also. If you take the markings here, so Australia, if you take Melbourne, it's about, I say 9 or 10. We say about 10,000 kilometers, 10,000 kilometers. And you know, the maximum distance that you can cover in a single hop is about 4,000, 4,200, 3,500. We'll say 4,000. So how many hops? 3 hops minimum. So that is if you are beaming at very low angles. So that will give you the propagation possibilities and all that. Well, I think we have rushed through a big
Yes.
presentation, Aranga.
Yes, Victor. And
I hope.
add in on one last point.
Yeah.
The first link, sadly, the screen isn't refreshed yet, but it will come anytime. Anyway, the propagation plotting map, we call them RF splat maps, as I remember. So there's this common website that we use, radiomobile.com. Victor Echo to Delta Bravo Echo.com. Victor Echo to Delta Bravo Echo.com, which provides a radio mobile software application online. We use it all the time to calculate and plot our propagation. Actually, the VHF propagation, or we use it mostly for repeater planning, link budgets, calculating link budgets, and to calculate the propagation and to plot them on a map. Okay, here's the screen. So you can go to that website also, be familiar with it, and if you need any help configuring that and the settings that you need to use, just reach out to us. And Victor, with that, we have come to the end of the presentation. You kept on going for more than 2.5 hours non-stop. Thank you very much. I know your throat must be hurting now, and it's been a real pleasure to have you do this entire presentation, Victor. We tried to cram in everything, the entire syllabus into 2 hours, 2.5 hours. I know that's difficult for viewers, the candidates, but don't get discouraged. I will share these materials with you, and you can go through them leisurely. And if you find anything difficult, you need any more clarifications, feel free to reach out to us. Yeah, Victor, would you like to add anything? I think we have some questions also.
Yes. What I would like to say is, we just gave you an overview or a synopsis or summary of HF propagation, and Taranga with Kusal have done this presentation with lots of information there. Now, thankfully, the internet is full of information. Now, if you pick up, for instance, you want to expand on what the OWF is, you go to individual items. It will give you so much information, and gray line propagation. There are number of websites, articles, or whatever. So you can expand. So we touched on this so that as an exam preparation to give you an insight into what it is all about on propagation. So you can do your homework and expand on it and be thorough with it if you want, or else you can use it as a guide and find your own information. So thank you very much, Taranga, and thanks for listening, and thanks for your interest. And if there are any questions here, Taranga, I don't know whether Vijay would have taken the net today, I suppose. Anyway,
completely forgot that. Dr.
One more
Singh,
thing, just Taranga, critical angle also, is it in our syllabus?
Yes. Critical. What is the critical angle? We say, what is the critical angle of refraction?
Minimum angle.
Yeah, the angle at which a signal is sent back to Earth. The sharpest angle where your signal will not go through the ionosphere. Right? If it is 86 degrees, then that will be, and then 87 will go through the ionosphere. The critical frequency, the angle is 86, right? The angle at which the signal is sent back to Earth. Okay?
Okay.
Is that clear? Okay.
Yeah, it's very clear.
Okay.
Thank you very much, Victor. Very insightful presentation. A lot of practical details. We understood a lot of things very well.
Yeah.
I know time was limited.
So anything else? Anything else? Of course, anytime you can call me or we can have a chat at any time at Sibatu for today. Yeah, Taranga, anything else?
Victor, I see Dr. Singh, 9 Mike 2 Kilo November is also around. I don't know whether he's listening. It must be very late for him. Dr.
Yeah,
Singh,
I acknowledged him at the start.
Yeah.
It was
Maybe
past
he's busy. Yeah. Any more questions? Anything තව මොන හරි කතා කරන්න තියෙනවද? ප්‍රශ්න මොනවා හරි තියෙනවද? මේක අපි discuss කරමු එහෙම මොනවද? Hari, seems like there are no more questions.
Taranga, what we
Yes,
can do is, we are going through various topics now towards our exam. So, as we come closer to the exam, if there are any topics that they would like to expand on or not clear or anything, we can have a final summary sometime and then, expand on it, okay?
Yes, that sounds excellent. Yes.
Okay, then that's it. So I'd like
All
to
right.
thank everybody
Victor,
who was interested enough to listen.
Victor.
Thank you, Taranga. Thank you, everyone.
Right. I will make sure that this presentation is available on the LMS. You can go and also I'll add some questions so that you can practice.